Hi friends, this is Rashekar, a GATE faculty for electrical machines. In this video, we are going to discuss about the previous GATE question. This is the question on switching transients. Say this question. A single phase transformer is switched to the supply to have minimum inrush current. Switch it to the supply to have minimum inrush current. The switch should be closed at. The switch should be closed at. Options are maximum supply voltage, zero supply voltage, 1 by root 2 maximum supply voltage, 1 by 2 maximum supply voltage. Let's see here. Generally, we know that the supply voltage and flux are 90 degrees displaced each other. Nothing but, for example, this is my supply voltage, then the flux should be like this, the flux should be like this, the flux should be like this. For example, if switch is closed at zero voltage condition, zero supply voltage, actually the flux also zero, but the desirable flux is maximum, but this is not possible because I closed my switch just now at V is equals to 0. When V is equals to 0, I closed my switch. At that condition, production of maximum flux is not possible. When the supply voltage increases, the flux also increases, the flux also increases to like this maximum. Nothing but when it reaches to 0, when it reaches to actual maximum, actually the maximum flux, but it reaches to 2 times of the maximum flux, this effect is called doubling effect. But if the switch is closed at maximum voltage condition, at this condition, voltage 0 as well as flux 0, our desirable flux also 0, actual flux also 0. Because here itself started, so then starting the flux increasing and decreasing. So if the switch is closed at zero voltage condition, it leads to doubling effect and magnetic inrush currents. Magnetic inrush currents are flows in the machine which are very dangerous. But if the switch is closed at maximum voltage condition, then there is no doubling effect, there is no magnetic inrush currents or minimum magnetic inrush currents. Now tell me which of the following is correct answer. The switch should be closed at zero supply voltage condition. Is it correct? No. If the switch is closed at zero supply voltage condition, it leads to doubling effect. That's why don't use this one. So where I have to close the switch? I have to close the switch at maximum voltage condition. If the switch is closed at maximum voltage condition, then desirable flux and actual flux is 0. So there is no doubling effect. There is a minimum magnetic inrush currents. So our answer is maximum supply voltage. Don't close the switch at 0 voltage because it leads to doubling effect, maximum magnetic inrush currents. Okay? See this question. The core flux of a practical transformer with a resistive load. The core flux of a practical transformer with resistive load. This is my transformer and here we have a core flux when it is connected to a resistive load. When load increases, load current increases. Nothing but I naught also increases, I mu also increases. When load increases, current increases, nothing but no load current also increases, and I mu also increases. When I mu increases, then core flux also increases. But how? Generally slightly constant is wrong answer. Increases linearly, decreases wrong answer. Increases linearly or increases as square root. Which of the following is exact correct answer? So in that, the core flux increases as square root of the load, increases as square root of the load. This is well preferable correct answer. When a practical transformer connected to a resistive load, when load increases, the core flux also increases, but not linearly. This increases with square root. This is the question. Just remember this, right? In this video, see this question. A 1 kVA 230 by 100 volts single phase 50 Hz transformer having negligible winding resistance and leakage inductance. Having negligible winding resistance and leakage inductance is operating under saturation. This is operating under saturation. While 250 volts 50 Hz sinusoidal supply is connected to HV side. On HV side, 250 volts 50 Hz supply is connected. A resistive load is connected to LV side of the winding. Resistive load is connected to LV side of the winding. What happens, sir? Here, like this is my transformer. Of course, this is HV side. Of course, this is LV side. Here resistive load is connected, but here supply is connected. 250 volts supply is connected, which draws the rated current. It draws the rated current. Which one of the following quantities will not be sinusoidal? Which of the following is not a sinusoidal? They are asking question. See here, in this condition, sinusoidal supply is connected to LV side, HV side, and a resistive load connected to LV side. Resistive load connected to LV side. Then which of the following quantity will not sinusoidal? See here, the voltage induced across the LV. This must and should be sinusoidal. But they asked quantity will not sinusoidal. This should be sinusoidal. This is wrong answer. Core flux. If the core flux is sinusoidal, then only the voltage across the LV is sinusoidal. And next one, load current. Load current may be sinusoidal or not, no problem. Generally, it should be sinusoidal. And next one, current drawn from the source. Yeah, the current drawn from the source, especially the magnetizing current drawn from the source, should not be sinusoidal. This should be a peaky wave. When the magnetizing current is peaky wave, then only the core flux is sinusoidal. Then only the EMF induced in the waveform is sinusoidal. Then only, so the current drawn from the source this should not be sinusoidal. The magnetizing current should be a peaky wave. Then only we can get the sinusoidal EMF. So, which one of the following quantity will not sinusoidal? The current drawn from the source will not be sinusoidal is the correct answer. The I mu value should be peaky wave, you know very well, right? This is the question they will ask you, right? In this video, see the question on efficiency. This type of questions are very important for competitive exams. Let's see. A single phase transformer has maximum efficiency of 90% at full load, maximum efficiency of 90% at full load and unity power factor, full load and unity power factor, efficiency at half full load and same power factor is, efficiency at half full load and same power factor is, they are asking question. So at max efficiency, iron losses is equals to copper losses. Let's try to calculate it. Efficiency 90% is equals to, what is kVA? We don't know kVA. kVA full load. What is power factor unity? Upon kVA full load power factor unity plus iron losses plus copper losses. Copper losses nothing but iron losses. So now cross multiply 90 kVA full load plus 2I, 2WI into 90, 2 into 90 into WI is equals to 100 kVA full load. From this WI, I want WI. So for that, just bring this inside. So 10 kVA full load upon, what is WI I want? 2 into 90. 2 into 90. 0, 0 gets cancelled. So the iron losses is equals to 1 by 18 times of kVA full load. Iron losses is equals to 1 by 18 times of kVA full load. We got this equation. Now calculate the answer. Half full load and same power factor. Efficiency at half load is equals to half into kVA full load into power factor upon half into kVA full load into power factor plus iron losses. What are the iron losses here? Iron losses is equals to 1 by 18 kVA full load. 1 by 18 kVA full load plus copper losses. Copper losses at half load, nothing but 1 by 4th of copper losses at full load. Do you know what are the copper losses at full load? The copper losses at full load is equals to iron losses, because at full load we got maximum efficiency. At full load we got maximum efficiency, so at full load copper losses is equals to iron losses, nothing but 1 by 18 times of kVA full load. Now simplify this. Simplify this. What is the answer here? The kVA full load by 2 upon, here 2 is there, here 18 is there, here 4 into 18 is there. So what is the LCM? 4 into 18 is the LCM. 4 into 18 is the LCM. And here only 2. So 2 into 18, nothing but 36 times of kVA full load plus here only 18 is there. So 4 times of kVA full load plus kVA full load plus kVA full load. Now tell me what is the answer? What is the answer? Here 2 ones, 2 twos are. So this 2 brings upside. 36 times of kVA full load upon 36 plus 4, 40, 40 plus 1, 41. 41 times of kVA full load. This kVA full load gets cancelled. So finally the answer is 36 by 41. 36 by 41 is our answer. If you calculate this 36 by 41, you can get 87.8 percentage. 87.8 percentage is our answer. Very simple. Just we have to calculate efficiency. From this efficiency, we have to find the iron losses, as well as this is equals to copper losses. Then find the half full load efficiency. Substitute here in iron losses and copper losses. Then simplify and get the answer. This is a big question actually. Without practice, we can't do answer for this question in exam. In examination, if you want to do the question, you have to practice them more and more, right? In this video, see this question on three-phase transformers. Let's see which three-phase connection can be used in the transformer to introduce a phase difference of 30 degrees, a phase difference of 30 degrees between its output and corresponding input line voltage. They want 30 degrees phase difference. So generally I said you, we have a different transformer connections, delta delta, star star, delta star, star delta. Apart from this, delta zigzag star and star zigzag star also is there. We saw already in delta delta and star star and in delta zigzag star, the phase displacement between input and output is only either 0 or 180 degrees. Yes or no? Even in delta star also 0 or 180 degrees. But in star delta and delta star and star zigzag star, the phase displacement is plus or minus 30 degrees. That is 0 plus or minus 30 degrees or 180 plus or minus 30 degrees. Now tell me, 30 degrees difference, in which it is possible? In star star not possible, in delta delta not possible, in delta zigzag star not possible, only possible in star delta in the given question. In the given question, it is possible only for star delta because we saw each and every connection and its angles, right? See this question on tests of transformer. Let's see, in transformers, which of the following statement is valid? In transformers, which of the following statement is valid? Let's see. First, see the options. In an open circuit test, copper losses are obtained, while in short circuit test, core losses are obtained. Option A. Option B. In open circuit test, current is drawn at high power factor. Option C. In short circuit test, current is drawn at 0 power factor. Option D. In open circuit test, current is drawn at low power factor. These are the four options. So here we have to discuss about OC test and SC test. OC test and SC test. In generally, in OC test, the main aim is to find the iron losses. In SC test, the main aim is to find the copper losses. And in generally, in OC test, the power factor is, the no load power factor is around 0.2 to 0.25 lagging. But in SC test, at short circuit condition, the power factor is around 0.5 to 0.6 lagging. I tell you already, I said you. So now to see here, which of the following is correct statement? In open circuit test, copper losses are obtained. Open circuit test, iron losses obtained, not copper losses. While in short circuit test, core losses obtained. In short circuit test, copper losses obtained. This is 100% wrong. Next one, in open circuit test, current is drawn at high power factor. In open circuit test, low power factor. In short circuit test, high power factor. So, in open circuit test, current is drawn at high power factor. Wrong answer. In short circuit test, current is drawn at 0 power factor. Is it 0? No, this is also wrong answer. In open circuit test, current is drawn at low power factor. In open circuit test, current is drawn at low power factor. This is 100% correct answer. So just by knowing the basics of testing, you can get the answer for this question. Don't confuse, read all the options carefully. Right? See this question on voltage regulation. In a transformer, zero voltage regulation at full load is. Zero voltage regulation at full load is. Option A, not possible. Option B, possible at unity power factor, possible at leading power factor, possible at lagging power factor. Which of the following is correct answer? Right? Let's see. Generally, voltage regulation formula per unit R into cos pi plus or minus per unit R into sin phi per unit R into cos pi plus or minus per unit x into sin phi. We know where plus for lagging load, where minus for leading load, and at unity power factor. Can you tell me what is voltage regulation at unity power factor? Unity power factor sin phi 0 cos pi 1. So at unity power factor voltage regulation is per unit R. So tell me, I given you voltage regulation curve also. In generally this is lagging, this is unity power factor, and this is leading. Always positive, nothing but at lagging load the voltage regulation is positive only. At unity power factor also voltage regulation positive only. Up to here positive only. Up to here positive only. But in leading load, voltage regulation sometimes positive, then after 0, and then after negative, nothing but in leading load positive regulation possible, 0 regulation possible, negative regulation also possible in leading load. Now they ask the question, 0 voltage regulation at full load is. 0 voltage regulation possible only in leading load. Only in leading load the curve crosses the 0. Only in leading load two terms are subtracted. When two terms are subtracted, it may lead to 0. So which of the following is correct answer? Possible, 0 regulation possible, no doubt, but only at leading power factor. Remember this question, very important, right? In this video, see this question on testing again. It is desired to measure parameters of 230 by 115 volts 2 kVA single phase transformer. The following wattmeters are available in the laboratory. First wattmeter 250 volts 10 amperes low power factor meter. Second wattmeter 250 volts 5 amperes low power factor meter. Third one 150 volts 10 amperes high power factor meter. Fourth one again 150 volts 5 amperes high power factor meter. The wattmeters used in OC and SC test of the transformer will respectively, which wattmeter is preferable for OC, which wattmeter is preferable for SC, they are asking. See here, generally OC test conducted on LV side, SC test conducted on HV side. Nothing but this is on 115 volts side and this is on 230 volts side. And In OC test, the power factor is low, low power factor is enough. In SC side, power factor is high, so high power factor we required. In OC, the current is less, low current. The current is I naught, which is very small current, less current required. But in SC, due to short circuit, current is more, high current required. So see here, low voltage, low power factor, low current. On HV side, high voltage, high power factor, high current. Let's see. For OC, which wattmeter is preferable? First of all, for OC, low power factor is preferable, high power factor not preferable. So low power factor is preferable. Low power factor is preferable, right? Next, here see, actually they given low power factor, okay, but they given 250 volts. Sir, we said that OC test should be conducted on LV side, but in the question they given directly LV and HV. LV and HV are primary and secondary. So we have to go based on the question. This is low power factor is 100% correct answer for OC, and the current should be minimum for OC. These two are 100% preferable for OC test. So we have to adjust with voltage. Of course, we are going to conduct test on HV side like that. No problem. So in this, the preferable answer is we have to choose. So low power factor 5 amperes is very preferable. That's why W2 is for OC test. W2 is for OC test. Option B or option D may be correct answer. W1 for OC test, wrong answer. W1 for OC test is wrong answer. Next one, for SC test. For SC test, high power factor is preferable. This for OC test and this for SC test. High power factor, okay. What about current? Current should be maximum. High power factor and high current. And voltage may be less value, no problem. So this W3 is for SC test. So 100% the preferable answer is option D. Nothing but this is for OC test and this is for SC test. This is for OC test and this is for SC test. This is the question on testing. Very, very important. Right? Thank you. Hi friends, this is Rashekar, a GATE faculty for electrical machines. In this video, we are going to discuss about the previous GATE question. In this video, see this question, listen carefully. A single phase 50H iron core transformer in the circuit has both vertical arms of cross-sectional area 20 centimeters square. The vertical arms having the cross-sectional area of 20 centimeters square. And both horizontal arms having the cross-sectional area 10 centimeters square. 10 centimeters square. If the two windings shown were wound instead on opposite horizontal arms, what they are saying? They are trying to wound these windings on opposite horizontal arms. Nothing but the modified transformer is the modified transformer is like this. Like this. They want to wound on opposite arms of horizontal arms. Opposite horizontal arms, the mutual inductances will. At this condition, what happens to the mutual inductances? What happens to the mutual inductances? Right? Let's see here. Let's see here. Generally, we know that inductance is equals to N phi upon I, nothing but N by I, phi nothing but MMF by S, MMF by reluctance. So the inductance L is equals to N phi by I. N by I, phi is nothing but MMF by S. Nothing but the inductance is inversely proportional to reluctance. Inductance is inversely proportional to reluctance. Reluctance is equals to L by mu A. Nothing but the inductance is directly proportional to 1 by S. S nothing but L by mu A. Nothing but the inductance is directly proportional to mu A by L. What happens, sir? Here the conclusion. The inductance is directly proportional to area. Inductance is directly proportional to area. Inductance is directly proportional to area. As well as mutual inductance also directly proportional to area. Inductance directly proportional to area as well as mutual inductance also directly proportional to area. So finally, mutual inductance directly proportional to cross-sectional area. Here what happened? Actually vertical arms are having 20 centimeters square. 20 centimeters square cross-sectional area. But now we are placing on horizontal arms which having the 10 centimeter square cross-sectional area. Nothing but the area, cross-sectional area reduced to half, as well as the mutual inductances also reduced to half because the mutual inductance is directly proportional to area. This is very simple question. So the answer is double. Wrong answer remains same. Wrong answer B oft. 1 by 4th also wrong answer. Simply the inductances and mutual inductances are same. Here inductance directly proportional to area. Then mutual inductance also directly proportional to area. Then when area reduced to half, and mutual inductance also reduced to half. This is the mutual inductance and area relation. Question based on that relation only. Did you understood? Right? In this video, we are going to discuss about a question. This is very important. They will ask you like a model questions. Let's see. Single phase transformer has a turns ratio of 1:2, turns ratio of 1:2, and is connected to a purely resistive load, is connected to a purely resistive load as shown in figure. The magnetizing current drawn is 1 ampere. What is that? The magnetizing current drawn is 1 ampere. And the secondary current is 1 ampere. Secondary current also 1 ampere. If the core losses and leakage reactances neglected, core losses and leakage reactance neglected, then the primary current is, then they want the primary current. Actually, what is the primary current? The primary current I1 is equals to I0 plus I2 dash. I0 plus I2 dash. Here I have I2 dash is equals to K into I2, where K is equals to N2 by N1, N2 by N1 of I2. So I2 dash is equals to 2 amperes. This is perfectly resistive. This is pure resistive current, pure resistive load current. So whatever, this is a 2 amperes. Next I want I naught. I naught is nothing but I naught is equals to square root of IW square plus I mu square, but there is no IW value. We have only I mu. 0 plus 1 square, that is equals to 1 only. I naught. Here IW 0, we have only I mu, nothing but this is pure reactive. Pure reactive. The resistive component is 0. This is pure resistive, this is pure reactive. What is the angle between them? 90 degrees. What is the angle between them? 90 degrees. So now I have a I2 dash and I have I naught. Then I1 is equals to square root of I naught square, nothing but 1 square, plus I2 dash square, nothing but 2 square, plus 2 into I1 into I naught into I2 dash into cos 90. Cos 90 is 0. Cos 90 is 0. So no need to take all these. We know if that is the phase angle is 90 degrees, then this is enough, like this. So I1 is equal to square root of 1 square plus 2 square. Nothing but 1 square plus 2 square, nothing but 5. Root 5. But the options are like this. Root 5 not equals to 2. Root 5 not equals to 3. Root 5 not equals to 1.41. Root 5 equals to 2.24. Root 5 is equals to 2.24 amperes. This is our I1. The very simple question. They given I2 and I mu. IW is equals to 0. Then I2 dash and I naught. Because I naught is equals to sum of these two, but IW 0, that's why I naught is equals to 1. Then I1 is the vector sum of these two, but here these two are 90 degrees displaced, that's why 1 square plus 2 square, that is equals to 2.24 amperes is our answer. Very important question. Right? Understood? Thank you.